Okay, good morning, everyone. I hope you survived well enough to yesterday's session. It was dense in the morning, and I guess it was dense in the afternoon too. So I hope it's not going to be too heavy today. The main theoretical framework was laid down yesterday. So today we'll go through data, and results. I gave a little bit of a historical character to my lectures. So I'm going through the way things evolved in time experimentally. And today we're going to get close to the present. We'll recap some results from the past before, and then get into the present. And the second lecture will be devoted to the future, to the perspectives. So what I will discuss right now is I've been focused all of yesterday on deeply virtual contour scattering to access GPDs. But as I said, this is not the only reaction that we can measure to have access to GPDs. We also can measure what we call DVMP, that is deeply virtual meson production. So I will start by talking about DVMP, and then I will move to the present and talk about the experimental program at Jefferson Lab at 12 GeV, focused on DVCS, but not only. So just recapping a little bit what we discussed yesterday. Yesterday, we mainly focused on the measurements that were carried out on DVCS at JLab at 6 GeV. And there was a wealth of results from both all B and all A, measurements of asymmetries, cross-section, target asymmetry, and so on. And basically, thanks to the fact that we measured all these observables, we started to get some insight into the structure of the proton, in particularly what we have obtained thanks to the first attempts to fit GPDs from the data. We have obtained a first tomographic image of the proton, some hints about the distribution of the pressure in the proton, and model-dependent extraction of, oh, there you are, good morning, of the quark contribution to the total angular momentum of the proton, and also some first ideas on the distribution of the GPD H tilde. So, as I mentioned yesterday, there are several reactions that can be measured to access GPDs. We focused a lot on DVCS yesterday, but there are other channels. And the concept behind, I mentioned it yesterday, is that GPDs are universal. So the blob that you see here that describes the neutron structure does not depend on the top process that is applied to it. So the processes I will talk about this morning to start with are the deeply virtual meson production that is described by the diagrams that you see here below. So deeply virtual meson production, again, the concept is similar to DVCS. We have a high energy electron that shares a virtual photon that couples with one of the quarks of the nucleon. However, this process is more complicated than DVCS because there isn't directly the propagation of the photon, emission of the real photon, and the quark that goes back in the proton. But what happens is that there is an exchange of a gluon and the formation of a meson in the final state. So this process is more complex. And the interpretation of this process in terms of GPDs is less straightforward than for DVCS. You remember the concept of factorization that we talked about yesterday, that the top part can be expressed in perturbative QED, and the bottom one is described by the GPDs. In the case of DVMP, the factorization has been proven only for longitudinally polarized virtual photons. And when we measure the cross-section, we need to make sure that we can extract the longitudinal component of the cross-section, and that is the one that we can interpret in terms of the four leading twist GPDs. So one beauty of the measurement of DVMP to extract the GPDs is that changing the kind of meson, we can have a different sensitivity to GPD. You remember yesterday we had depending on which observable of the VCS, we could be sensitive to different GPDs. Here, the idea is you change the kind of meson that you measure and you have a different sensitivity to GPD. So if you measure vector meson, you are sensitive to the GPDs H and E. If you measure pseudoscalar mesons, you are sensitive to the tilde ones. Also, another nice feature, again, making the parallel with DVCS, yesterday I said that if we want to decompose the flavor dependence of the GPDs on DVCS, we measure DVCS on the proton and DVCS on the neutron. Yes, here you are. I think the kinematics are probably different.
It's the same exchange of parameters.
Yes. So, what was I saying? Yes, the quark composition of the mesons is different. So by measuring different mesonic final state, we access different combinations of quark GPDs, and then combining them, you can extract the individual contribution for the U and the D quarks. So as I was saying, the diagram is more complicated than the DVCS one. And if you look at the distribution, at the dependence of the amplitude for the longitudinal cross-section for this process, there is a dependence on the GPD that you see here, but there are also complications that come in. For instance, there is a part depending on the effective scale of QCD alpha S, and there is this distribution amplitude that it's another soft, as we say, function that describes the formation of the meson. So the expression and the extraction of the GPD is, from DVMP is even more complicated than the case of DVCS. So there has been a lot of activity with JLab at 6GeV, in particular with class in the measurement of deeply virtual meson production. So here you have an expression of the fourfold differential cross-section for a meson production, and you see there is a factor here that is the virtual photon flux. It's just a function of Q squared X Bjorken and E. And then you have a linear combination of different structure function for different types of polarization of the virtual photon. And this expression depends on the phi angle that I already introduced yesterday, and it's the angle between the leptonic and the hadronic plane. So there has been measurements class both for vector meson exclusive electroproduction and pseudoscalar meson exclusive electroproduction. You see them listed here. The nice thing experimentally about measuring DVMP is that the cross-section is much bigger than DVCS. So on paper, at least the measurement, it's easier. You're looking at something that has more probability to happen. You see the cross-section here are at the level of the microbarn, while yesterday when we looked at DVCS, it was a nanobarn or picobarn level. However, as I said before, the interpretation in terms of GPD is more complicated, and also the kinematic regime. Yes. Well, I said it in the slide before. Because the GPDs are not the only soft object that enters in the amplitude. There is also the formation of the meson itself that enters. So there are two kinds of structure, of phenomenological objects that need to be taken out from the amplitude. And this one needs its own parametrization. It's to be
greater than DVCS.
Yes, so to measure it, it's easier, but then to get the GPDs out of it, it's more complicated.
And why would that be the case? In the case of a DVCS, you would have a photon in the final state.
Yes, so the formula of DVCS here has the amplitude as only the GPDs and then kinematic factors.
I'm still trying to understand why there would be more probability to get a photon instead of a meson there.
No, there is no more probability to get it. I mean, the cross-section for DVCS is smaller than DVMP. So the probability in principle is bigger. What I'm saying is that it's more difficult to extract the physics that we want out of this channel because it has an additional complication, another part that we cannot constrain perturbatively, that is this formation of the meson. So it's a theoretical difficulty. Experimentally, it's probably easier to measure, but theoretically it's more difficult to interpret in terms of GPDs.
Yeah, and just one.
Yes.
And the process, just getting a photon in the final state
Yes.
versus a meson in the final state. Which process has more cross-section?
The cross-section is bigger for the DVMP.
And why is that?
Why is that so? Sure, why is that so? It just happens to be that way. Cross-section that comes out bigger.
So what happens with the Western photon? There is a electron exchange between the quark and the proton. That's how you get a meson. I'm trying to see like why would that?
Why the cross-section for DVCS is smaller than the DVMP? It's a good question, and I'm not sure of why. Oh, that I have to look into it. But anyway, that makes it easier to measure in a sense. However, yeah, as I said, it's more complicated, and what is not fully clear is which kinematic condition we need to make sure to be in the factorization handbag regime. And what the data seem to tell us, the data that were taken at JLab, is that we are not yet, at least at the Q-square and the kinematics that were available at class 6GV, we were not yet in the regime in which we could interpret the data with the GPDs. In fact, you see here some cross-sections that were measured for the ρ0 channel, and you see the measured points were here for different beams in Q-square and plotted as a function of W. And the curves that you see, the solid curve, it's some twisted thing that we don't go in detail in, but the other curves are GPD-based model, and you see that all the GPD-based model fail to reproduce the rise of the cross-section at low W. So this thing we are going to get back into. By look, here we can see a comparison of the world data taken in kinematics similar to the JLab ones for different vector measure final states. You see we have data for ρ plus, ρ0, omega, and phi, and for the ρ plus, ρ0, and omega, there is this increase at low W of the cross-section that is not observed for the phi. And then there is this flat region at high W, and we'll get back on that in the next slides. Here we can see a comparison of the total cross-section for different channels of vector mesons. So here we have the ρ0, here we have the omega, the phi, and the j psi is here. So what you can see is that for the ρ and for the omega, there is this part, this dropping part that I mentioned earlier at low W, followed by this straight region when W is increasing. Increase of W also correspond to increase of Q square. And the measurements at JLab are all focused in the low W region, while the high W region measurements are coming from Hera mainly, Hermes and Zeus and H1. So what some colleagues did, they looked at this trend and they fitted the distribution of the cross-section with this sum of two terms with two exponential, and one exponential that describes the drop of the cross-section at low W, and one the increase at high W. And so it seems like the ρ and the omega have a specific trend of dropping cross-section at low W that is not matched by the heavier meson, the phi and the j psi. And this is something that still has to be understood. And so these two different slopes for the different kinds of meson is not understood. And if we look at the models made based upon GPDs, they all fail to reproduce this increase of the cross-section at low W. So this is something that has not been understood. It could be the sign that at the kinematics that correspond to low W, we are not yet in the regime where the factorization for the GPDs can be applied. So what you see from the models that are shown here to reproduce the data for rho 0 and phi. It seems like it's necessary to include at high W the contribution of gluons to reproduce the cross-section. So in this case, the dominant diagram would be this one. So it seems at high W and Q square, GPD models that are based on gluons can reproduce a cross-section, but at low W, the GPD regime doesn't seem to be applying, at least to the rho 0 and omega final state. Yes. Yes.
Without everyone saying. So the final
Yes, that was the quark.
Yeah, excellent. So the final vectorism that you get, where is it in kinematics? Where is it mostly found? Is it close to the nucleus or?
The distribution, it's not like yesterday we had the beta iter that was supposed to be mainly in the forward direction. In this case, there isn't constraint of that.
Okay, and is it, so there is no more other particles, like that's the only new final state, like the new particle that is in the final state. So there is.
It's exclusive, so you know what you're measuring.
Yeah.
Final state, you have the rho 0 and the proton. That's all.
You don't detect the electron.
Yes, of course. I mean, yes, the lepton, the scattered lepton is always there. It's what helps, makes us define Q square and the kinematic variables of the electron level. So,
Okay.
so yes.
Yeah.
Okay, so this is just to finish on the vector meson, the situation is not clear. So the data at 6 GeV don't help us to understand if we can apply the GPD formalism to these final states. So it's not really a happy ending so far for the history of mesons. On the other hand, yesterday, I remind you that when I introduced the GPDs, the 4 GPDs that we talked about yesterday all day, I mentioned that there are some approximations that make us tell that the DVCS process is described by these 4 GPDs. Among this approximation, there was the fact that we assume quark helicity conservation. So what this means is that the top arrows that you see here that refer to the helicity of the initial and final quark are pointing in the same direction in the initial and the final state. So there is no helicity flip between the initial and final state. And this approximation that we don't have a helicity flip between initial and final state, which is the conservation of the quark helicity, holds well for the DVCS case. But let's see if it's the same case for DVMP. So in general, if we forget about the approximation of helicity conserving quarks, we can have 4 additional GPDs that are the so-called chiral odd GPDs that allow for the helicity flip of the quark between the initial and the final state. And here you see diagrams equivalent to the ones I showed for the other 4 GPDs for the helicity flip GPDs. They are called HT, H tilde T, ET, E tilde T, and T is a subscript that stands for transversity GPDs. So they are called either chiral odd or transversity GPDs. So in general, these are complicated to access because in DVCS, this helicity flip process is not dominant. And there are no constraints basically to help us parameterize them. You remember yesterday, I said the ordinary GPDs reduced to the PDFs in some limits are integral of the form factor. So we have some known measured quantity to which to refer to start parameterizing. Instead, this is not is not possible with the transversity GPDs. There is some link to the transversity PDF that describes the distribution of transversely polarized quark in a transversely polarized nucleon. But this is more or less all we have. So here, there is a table that summarizes the kind of GPD depending on the polarization of the quark and the polarization of the nucleon. And you see the transversity GPDs are here. There is a combination of transversity GPDs that correspond to transversely polarized quarks and unpolarized nucleon, and then longitudinally polarized nucleon and transversely polarized nucleon. And here you see a comparison between the spatial distributions of quarks. You remember the concept of tomography that we talked about yesterday, that you can get the distribution of the quarks in the transverse position plane. And so here it's some lattice QCD calculation that shows for up quarks and down quarks how things look like if we are looking at basically in the z-axis here, you're looking at the GPDE for these two plots, which describes the distribution of unpolarized quarks in a transversely polarized nucleon, while here you see how the GPD-ET, which describes the distribution of transversely polarized quark in an unpolarized nucleon, looks like. So this is the kind of pictures we could get if we could measure transversity GPDs, chiral odd GPDs. So a candidate that appeared the right one to constrain transversity GPDs, and this was found out experimentally, is the exclusive pi-zero electroproduction. You have here the expression of the cross-section that I introduced already beforehand, which contains this virtual photon flux, depends on the beam degree of longitudinal polarization. You see it here. And there are different structure functions that combine the cross-section. And at leading twist, this is the expression that we have for the longitudinal part of the cross-section. As I said, the longitudinal cross-section in principle can be expressed as a function of the 4 standard GPDs. And you see it here. But given the fact that H tilde is as opposite signs for the U and D quark, this part here is kinematically, I mean, it's suppressed. So the sigma L for the pi-zero cross-section is supposed to be small, and the sigma T and sigma TT terms of the cross-section can be expressed as a function of the transversity GPDs. So there are different models that make predictions for the cross-section of pi-zero, like the Goloskov-Kroll model, UT Goldstein, and they all predict a smaller longitudinal cross-section than the transverse one. This was verified by the measurements that were made by the class collaboration in 2012. So you see here some distributions for as a function of Q square, X Bjorken. It's each square, sorry, correspond to a different Q square X Bjorken bin, and you have T distributions for the different components of the cross-section. You see the blue in particular is what we are looking at. The transverse part of the cross-section seems to be very big and much bigger than the LT part of the cross-section. So this was a first hint that transverse cross-section could be important for pi-zero, and this was later confirmed by a measurement made in OLE, which is what is defined as a Rosenbluth separation of the sigma L and sigma T terms of the cross-section. You see here in the cross-section, the phi dependence is in front of this LT and TT terms, while the term sigma T plus epsilon sigma L doesn't depend on phi. So if you just look at the phi dependence of the cross-section, you extract this first term as a constant. So you cannot separate the two contribution of the transverse and longitudinal part of the cross-section. But Rosenbluth separation is a technique for which you run an experiment at different values of the beam energy, and the beam energy enters in this coefficient epsilon. So what you do, you vary epsilon, and you do the phi fits of the cross-section. So basically, you can extract separately for combining the measurement for different beam energy, the sigma T and the sigma L part. So what was shown by the OLE measurement is that I forgot to put the labels. I'm sorry. So yes, so here the red point on the top are the sigma T cross-section, and the sigma L is the bottom one. I'm sorry if I didn't label them. I will blame again that it's the older version of the slides, which it's not the case. So yeah, so this is an experimental proof that the transverse part of the cross-section for pi-zero is dominant. So this opens the way to study transversity GPDs by using the pseudoscalar exclusive production of pi0. And similar results were obtained also by looking at the eta exclusive production with class 12, and there are comparisons that were made between the pi0 and the eta final state. And according to models that are based on chiral odd GPDs, this ratio is expected to be about 1/3, and this was roughly verified by experiment. So what this means is that both, I mean, still it's a model-dependent conclusion that we get, because we cannot explain this kind of cross-section with the standard GPDs. So we assume that we need the transversity one, and then we get models that are based on transversity GPDs that reproduce the cross-section. So it's what we call a model-dependent statement. Still, if this is true, we can, in principle, perform the flavor separation of transversity GPDs, combining the results on pi0 and eta. So let's come to the present now, because all this was the old Jefferson Lab. But since then, there has been the energy upgrade of JLab with the doubling of the electron energy that goes up to 12 GeV. A new hall was built, as some of you know very well. That was the hall D, which is here. And the three experimental halls that are focused on nucleon structure studies are the halls A, B, and C. I will mainly show results from all the halls A and B, because hall C has yet to start the experiment dedicated to the DVCS and pi0 production. So I will give an outlook of the DVCS program for class 12 GeV. So there are different observables that we are going to measure or have been measured by experiments, both in all A with class 12 and with all C. So proton DVCS will have measurements of cross-section, difference of cross-section, beam spin asymmetry, longitudinal target, single and double spin asymmetry, transverse target, and then there are measurements also planned or done on neutron DVCS and target asymmetry for neutron DVCS. So as you see here, there are experiments that have already been done, and some have already published. Others are taking data or just finished or are planned for the short-term future. Again, as I said yesterday, the interest of measuring in different halls the same sort of process is that the different halls have different properties, luminosity, different coverage, different detector setup, and this allows to tackle different aspects of the observables we want to measure. So here are recent results that were published by Holei at 11 GeV, a bit less than 11, but okay. And these were high precision cross-section for DVCS on the proton cross-section and the differences of cross-section. And what was done here was a similar thing to what was done for the pi0 that I showed earlier, a kind of Rosenbluth separation of the cross-section. In this case, measuring a different beam energy allows to distinguish between DVCS and beta Heitler contribution to the cross-section, and you see it here in the fitting functions that are shown. So they can subtract the contribution of beta Heitler and single out the DVCS square term. And these data were so precise statistically that some GPD extraction fits could be done, and that they allowed to get some sensitivity on all the four quantum form factor. So this is something very peculiar of the Holei experiment, thanks to the high luminosity of the system. So for class 12, that is the new class detector after the upgrade, measure DVCS on the proton asymmetry, and this is the kinematic coverage that was obtained. Basically, with class 6, we would have something up to here. So this is the extra kinematics that are allowed thanks to the upgrade. This was a measurement of spin asymmetry for proton DVCS on a very fine kinematic grid. So what happens is that there are some bins that overlap with previously measured. In that case, the new data allow to constrain more strongly the GPD and the extraction of GPD, and then there are several kinematics that were never covered before, so this will allow to extend the kinematic coverage of GPDs. But as I said at the beginning, beyond DVCS and beyond DVMP, there are other final states that can allow us to measure GPD. One is the time-like quantum scattering. Time-like quantum scattering is the time-reversed process of DVCS. In DVCS, we have the virtual photon in the initial state and the real one in the final, while in TCS, we have the opposite, the real photon in the initial state, and then we have a virtual photon in the final state, which then decays in a pair of leptons. So as for DVCS, there is also the added complication in the final state that beta-Eitler interferes. And again, this interference can be exploited similarly to DVCS to extract interference terms that are connected to GPDs. So the expression is pretty complicated, but what I want to point out is coefficients M plus, minus, minus, and so on that you see here contain the linear combination of quantum form factors, similarly to what we had in DVCS. And what was done is that class 12 provided the first ever measured TCS result. It was not measured before. This is because it's a complicated final state to measure, and again, the cross sections are small. So you see here the final state topology that was done. We didn't have a real photon beam in hole B. So here, in principle, you would need the real photons hitting on a proton, virtual photon in the final state, and a proton, and the virtual photon decay in a pair of electron positron. But as we didn't have the real photon beam, what we did is doing quasi-real photoproduction, which means that we have an electron that is scattered at really very, very, very low angle and very, very low Q square. So this is real photoproduction would be Q square equals 0. Quasi-real is very close to 0. So this is obtained by making kinematic cuts that allow us to select the kinematic of the final state for the Q square close to 0. So there are two observables that were measured for TCS, the beam helicity asymmetry, and this is shown to be sensitive to the imaginary part of the quantum form factor H. And what was interesting in this measurement, okay, the error bars are very big, and this reflects the fact that it's small cross-section and process. But what was interesting of this is that this is the first sign of universality of GPDs, because this result that was obtained for the helicity asymmetry was compared to models of GPDs that reproduce DVCS. And this model turned out they reproduce also TCS. So it's the first time the same GPD reproduces two different processes. So it's a first sign of a first proof of universality of the GPDs. And then there was another observable that was constrained forward-backward asymmetry, that it's sensitive to the real part of the quantum form factor. And what was shown in this case is that comparing the result obtained to models that had or didn't have that D term in the parametrization of the GPD. D term, I talked about it yesterday, was that additive constant that we had that was related somehow to the pressure distribution in the nucleon. So basically, it seemed like without the term, the models could not fully reproduce the dependence of this asymmetry. So this shows that this channel is potentially promising for the understanding of the pressure distribution in the nucleon. So basically, these two reasons, the universality and the sensitivity to the D term, show the importance of TCS for the physics of GPD. As I said, it has a very small cross-section process, so these are very low statistics measurement. We would need higher luminosity to perform a more precise measurement. And then comes my favorite. It's the experiment to measure beam spin asymmetry for neutron DVCS. If you remember yesterday, at the end, I was talking about the fact that neutron DVCS is basically one of the few reactions that can give us access to the GPDE, which is the least constraint and the one that we need if we want to measure the sum rule that expresses the quark angular momentum contribution. So there were results shown yesterday from Hall A, and one thing that Alberto was asking was about final state interaction and that sort of things. Hall A didn't measure the recoil neutron to make the NDVCS measurement. They subtracted the deuterium data and the hydrogen data to get the contribution of the neutron. And this induces several systematic uncertainty, while what we did for class 12, we built a dedicated neutron detector to cover the regions of kinematics where the DVCS neutron is supposed to go. And it's here, and I love it because it's the detector we built in my group, so I had to put a photo. And this detector was installed in class 12, and we took data with a deuterium target, and basically we do a fully exclusive measurement in the final state. So there is no more the need to subtract data from hydrogen and deuterium, but sorry, this thing on the top is covering my reaction, so you cannot see it. There you go. So what we do is we measure the active neutron, the electron, and the proton in the final state, and then we reconstruct the missing proton by kinematics. So what we did, we finally extracted the beam spin asymmetry. You see it here. It's the phi distribution for one particular kinematic beam, and then we got the slope, sorry, the phi amplitude, sin phi amplitude of this asymmetry as a function of the relevant kinematic variables. So this is the first time the NDVCS is measured in a fully exclusive final state, and the statistics are small for a series of reasons. The cross-section is smaller than proton DVCS, and the detection of the neutron has lower efficiency than the detection of the proton. So combining all this together, and the asymmetry itself is much smaller than the one of DVCS on the proton, which is about 25%, while this is about 7 or 6%. Still, this is an important result. Yes. Yes, we have a scintillator barrel. So it's 3 layers of scintillators that surround the target, and the neutron interacts in the scintillator by elastic scattering on a proton. So what you measure is the scintillation light that comes from the excitation of the proton in the plastic. It's something that has the simplest probably concept for a neutron detector, but the efficiency is not a lot. It's estimated to be about 1% per centimeter of scintillator that you have. And given to the fact that this detector is, there were space constraints when we built it. There were other detectors that were already filling the space, and we only had 10 centimeters left in which we could put our detector. So we have a detector that is 10 centimeters thick. This means 10% of efficiency of neutron detection. So this makes it not very, it's a low efficiency for the detection of the final state. Sorry, I couldn't hear you.
0 degree calorimeters.
Okay.
Is it the same?
No, I don't think so.
And did you say the width or the radius of that thing?
Yes, this picture, it's not the best to show, but okay, these are just the light guides with the PMTs outside, but here there is a barrel. Basically, it's 3 layers. It has a segmentation because you want to be able to determine the position, the angles, and so on, but it's the bars are this long and this thick, and they are stacked up in 3 layers. I can take you to see it if tomorrow if they allow you. Well, you don't really see it because it's covered with the other detectors, but. Sorry, I cannot hear anything.
Does it agree with the OLE data with the subtraction of?
Well, the OLE data measured cross-section, not between asymmetry. So I think they also measured cross-section differences. So we could, in principle, combine their measurement of cross-section difference with the total cross-section, but then again, the kinematics are not necessarily the same. So a direct comparison is not, we haven't done it yet. So as this says here, it's a preliminary measurement that is not yet released, but what I wanted to come to was that this has been used by theorists to start to extract quantum form factors. So there is a group that is working on neural networks applied to the fit of quantum form factors, and they combine the OLE results for proton and NDVCS with the ones that we took for proton and NDVCS. And you see here, these two plots have on this side we have H, on this side we have E, imaginary part, real part, imaginary part, real part. On the left column, we have the unseparated GPD, so the GPD for the nucleon. And then here you have the quantum form factor separated in flavor. You have the red, that is the U, and the blue is the D. So what the data that we have made with class 12 bring the first possibility to start to separate the U and D quark in the E, both the imaginary and the real part of E. So this is something that shows the potential of this data. So we are trying to finish the analysis and complete also the extraction of the CFF this way. So just a little advertisement, the experiment we just finished to run at class 12. This was to measure the VCS both on the proton and the neutron with a longitudinally polarized target. And this would allow us to do the first time measurement of the target spin asymmetry for NDVCS. So for NDVCS, so far we just have cross-section and beam spin asymmetry. And these two observable, the target, single asymmetry for the target and the double asymmetry for the target, would have sensitivity to the H and E quantum form factor for the neutron. So this would also help us in separating the flavor dependence of H and E. So this experiment had the complication to have a longitudinally polarized target, and it again relies on the neutron detector that I introduced in the previous slide. And you can see here, as you remember in my first talk yesterday, I was showing pictures of Nobel Prizes and other major names for our field. So here you have the student that is doing most of the analysis for this experiment, and she's here. So I wanted to make her blush, and she's here, and you'll hear her name in the future, of course, when we will finally have the results coming out of this experiment. So here is an exercise that I did some time ago to understand the potential of the class 12 program to constrain the flavor separation of quantum form factors. So I put together projections for all the experiments that were planned to be done for class 12. I used the projection from the proposal because we had not yet done the measurements at that stage, and combine them and apply local fits to extract the quantum form factor, put together both proton and neutron results, and got quantum form factor for H and E separated. Here you see the different contributions for the, okay, here it's proton and neutron, sorry, the black and red, and here it's the quark U and D. So you see at the end of the whole class 12 program, we could aim to have this sort of precision on the separation of the quantum form factor. This was just something to give an idea. Of course, you see, we are going to get the precision where we would most want it. It's at low T, because the G-sum rule that expresses the quark angular momentum is supposed to be the limit at T equals 0. And that's where our error bars are the biggest. So we will not probably be able to say the very, very, very final word on the G-sum rule, but we will advance in that direction. Just to finish, you remember I talked about pi-zero electroproduction this morning as a possible channel to measure transversity GPDs. And there was a recent measurement that was done in Hall A that confirmed at 10.6 GeV, that again confirmed the fact that the transverse component of the cross-section is quite big. And so this confirms the trend that we observed in the 6 GeV data, that there is the dominance of transversity GPDs. So I summarize. DVMP is another way to measure GPDs beyond the VCS, and it gives the possibility to separate the flavor dependence of the GPDs, changing the kind of meson. And we had different measurements at 6 GeV at JLab, but for vector meson, most of the current data show that we are not in a region where we can yet apply the leading twist handbag formalism. And this seems to be only valid at very high Q-square and very low X-Bjork, and where the gluon dominates. On the other hand, the pi-zero and eta electroproduction emerged as good channels to constrain the transversity GPDs. So there is a new opportunities to have information on this kind of GPDs. And DVCS and DVMP measurement have started to come out from the 12 GeV upgrade. We have high precision cross-sections for DVCS and pi-zero from Hall A, and spin asymmetries from class for proton DVCS, and also the new ones from neutron DVCS, which allow the flavor separation of Compton for factors. And we also measure for the first time time-like Compton scattering, which shows the universality of GPDs and the relevance of this channel to determine the pressure distribution in the proton. This is all I had for this morning.